side and geometric mechanics and control from the other side. And luckily, the two domains intersect nicely in some applications, like micro air vehicles that fly like insects and birds. So today I will, discuss one result from each team. Probably we'll start with the one on vibrational stabilization and insect flight. Here is the main character in our discussion today. This is a oops, the video doesn't work quite. The video is not working. Let me see. You click on it. It's usually should work without clicking. It's not working. Okay.
Can probably access the full screen mode and play.
Let me try again. No. It's weird. Yeah, okay. Yeah, good. So this is a slow motion video for the hawk moth insect and hovering. So basically, insects, unlike birds, they move their wings back and forth, not up and down. And they move their wings very fast. This is a slow motion video. So if we try to analyze the mechanics of an bio-inspired flight, at the beginning, we adopt some assumptions to simplify analysis. If you neglect wing flexibility of the wing and the wing inertial forces, then you will realize that the equations of motions are exactly the same governing conventional airplanes. So this is why we're happy, because this set of equations has been studied for decades. We have huge legacy to exploit. These are inertial and gravitational loads, and these are aerodynamic loads, and the exact same taxonomy of airplane flight mechanics. But there is always but. The issue here is that these aerodynamic loads are essentially time varying, unlike conventional airplanes, because as you saw in the video in the last slide, the insect accelerates the wing and then decelerates because it has to come to a complete stop and changes the angle of attack throughout the cycle. All of these factors, they lead to essentially time varying aerodynamic loads, even at equilibrium. So if you want to represent the system in an abstract form, it will have explicit time dependence on T. And once you have explicit time dependence, we're not happy anymore, right? Because explicit time dependence makes the stability analysis and control design more challenging, even for linear systems. If you have x dot equals ax, everybody in this room knows by heart that if all the eigenvalues of the A matrix lie in the left half plane, the system is exponentially stable. But if you have A of t times x, if all the eigenvalues lie in the left half plane for all time, it doesn't guarantee stability, right? So unfortunately, we have explicit time dependence. And if we express our aerodynamic loads, which has dependence on time, linear in the state variables, linear in the motion variables, we will have this system. But forget all these details. The main take-home message is you will realize, or you will note here, that we used two symbols, T and tau, to denote the independent time variables. And this is to stress the fact that we do have two time scales. A fast time scale for the flapping motion and the associated aerodynamic loads, and the slow time scale of the body motion. And to give you an idea about that, you as a human being with your bare human eye, you will be able to track the motion of an insect from one point in the space to another. You can track its trajectory perfectly fine, but you will not be able to trace the motion of their wings. They move their wings very fast. So we have two time scales. And what about the ratio between these two time scales? Well, for one of the slowest flapping insect, the hawk moth, the ratio between the flapping frequency, which is the forcing frequency, to the natural frequency of the dynamics is 30 times, which is pretty large. Try to imagine this. You have a body like this or whatever, and you're trying to excite it with a varying force. And this varying force is too fast. It has a frequency that is 30 times its natural frequency. So most likely, this is well beyond the bandwidth. Most likely, this body will not feel these oscillations. It will only feel the average values. So this actually invoked averaging. Biologists who started doing this, they said, this is too fast to affect the dynamics. The insect feels only the average values of the aerodynamic loads, not the oscillatory components. Now, if you average out over the fast time scale, you get quantities over bar here, means average it. And there is no more tau, no more fast time scale. We got rid of the fast time scale. No more explicit time dependence. This system is time invariant. So you can do whatever you like. Yes, it's still nonlinear, but you can always linearize, check the eigenvalues. And here you can have two eigenvalues. You can see that there are two eigenvalues in the right half plane, indicating that the system is unstable. And this has been done by tens of papers. In fact, this is a kind of fact among flapping flight dynamics community. Insects are unstable at hover. And this made sense at the time, because if you look at what's the main source of instability, it's in the pitching motion of the insect. And why is that? Because they don't have pitch stiffness. CM alpha, I don't know if you're familiar with this term, but they don't have pitch stiffness to restore it when they get a disturbance. In fact, helicopters are unstable for very similar reason. So to an aeronautical engineer, an insect hovering over a flower is very similar to a helicopter hovering in place. And both are unstable for similar reasons. Everything made sense at the time, except that, we as engineers should have a mathematical justification of what we're doing. We should have a stability certificates, like in the language of control theoreticians. So if you dig more in the math of time periodic systems, here is the theorem. You'll find some theorem. F is periodic in time, so you can integrate it over the cycle to get the average of it. So this means that you converted a time periodic system into time invariant system. And if you had a periodic orbit here, now it reduces to an equilibrium point, fixed point. Of course, analyzing the stability of fixed point for time invariant system is much, much easier than analyzing stability for periodic orbit for time periodic system. And here is the mathematical statement of the theorem. For a small enough epsilon, stability of the fixed point implies the stability of the periodic orbit. A very powerful theorem that may seem to support the work of biologists. Powerful because you got to analyze stability for an easy system, but conclude the stability for a difficult system. But it says, provided that epsilon is small enough. So what is epsilon? Epsilon here goes by the reciprocal of the flapping frequency. So for high enough flapping frequency, hopefully epsilon is small enough, and which is the main intuition behind averaging. High frequency vibrations will not affect the body. But the question is, how high is high enough? How small is small enough? I did not find a more expressive statement than this in the Bible of Averaging by Sanders and Verhelst. They said, to many physicists and astronomers, averaging seems to be a natural procedure, very natural procedure that people do not even bother to justify the process. However, it is precisely the fact that averaging seems so natural that obscures the pitfalls and restrictions of the method. So we need a more rigorous mathematical analysis tool that either supports or refutes the work of biologists. And if you dig a bit more in the math, you always find Russians behind the scene, right? So this is Agrachev and Kamgrelidze, two Russian mathematicians. They wrote this paper in the honor of the 70th birthday of Pontryagin, the founder of optimal control theory. In this paper, they developed a new calculus for time-varying dynamical systems. It's called chronological calculus. And later, Sarachev, another Russian mathematician, and this is Patricio Vela. This was his PhD dissertation under Marston Caltech. They used these tools to develop what they called complete averaging. So what's the point here? If you have a system on this form, F is periodic in time, its complete average dynamics is not just integral over the cycle. It's actually an infinite series. The first term, lambda 1, is the integral over the cycle. But there are more terms. For example, the second term is the integral of some bracket. This bracket is a bracket between F and its integral. The bracket is the Lie bracket, which is just differentiation with respect to the states. So the take-home message is that I can compute as many lambdas as I want analytically, because it's just differentiation and integration. And here is the powerful statement of the theory. If this series converges, then stability of the fixed point implies stability of the periodic orbit, irrespective of epsilon. So there is no approximation here, and this is why they call they call it complete averaging. If your epsilon is very small, such that epsilon square is indeed negligible, and you're going to truncate after the first term, you recover the direct averaging theorem, which is known. But if not, you need to go higher and higher until you capture the required accuracy. And this is what we did. So these are the eigenvalues of the system I showed at the beginning. The red cross are the first order averaging. You see two eigenvalues in the right half plane indicating instability. But when you account for higher order terms, you know, these are, remember, these are zero mean signals. They are zero mean signals. You might think they do not have an impact. They are zero mean, perfectly zero mean. And they are very high frequency, 30 times the natural frequency. So it's quite legitimate. It's, you know, intuitive to think they do not provide, you know, a significant contribution. Yet they shifted all the poles, all the eigenvalues to the left half plane. So on the average, the system is unstable, but these high frequency vibrations of zero mean, they induce stabilizing mechanism. The good thing is this is an analytical approach, so we can look at things term by term to see how, you know, what is going on. So for example, here is the system matrix of the first order averaging, and here is the system matrix for second order averaging when we add more terms. Good, we can compare term by term to see what's going on. Of particular importance is this term because it was zero here. So it was solely created by high frequency vibrations. So let's try to recall the system structure and to interpret the meaning of this term. This is third row, Q dot, and fourth column due to theta. So this reads as follows: Q dot or theta double dot. So it's a pitching acceleration. If you multiply by moment of inertia, this means a pitching moment. A moment due to an angle or a force due to a displacement. This is a spring action, right? This is a spring. It's a moment equal negative k theta. That's the spring constant, actually. So, so these high frequency vibrations of zero mean that you neglect when you do direct averaging, they induce a spring action, a stiffness mechanism that brings the insect to its equilibrium when it's disturbed. And in fact, this is not the first time to observe a vibrationally induced spring. Here is the famous example of the inverted pendulum. It's unstable. If you leave it, it falls down. But if you vibrate the pivot, it becomes stable. So look at this. We will give it a disturbance now, and it resists the disturbance, and it comes back exactly as if there is a torsional spring here, but really there is no torsional spring. And if you do the same math, you will see that the effect of vibration appears as if there is a torsional spring. So which is pretty cool. In fact, we made this demonstration. We had this, still have it in the lab. We made it like a few years ago for demonstration purposes to play with it, and also for high school, you know, high schoolers visit the lab or any visitor to play with it. And then we realized a couple of years afterwards, we realized something interesting happened. So the Royal Swedish Academy, in their paper that you know, introduces the contribution of the Nobel Prize in Physics to people, they actually it seems that the contribution that deserved the Nobel Prize in Physics had to do with high frequency vibrations of laser. So they want to tell people about the high frequency vibrations. So they mentioned this, the Kapitsa pendulum, the inverted pendulum, which is vibrating. And it seemed that they did not find a better, you know, demonstration to cite in the paper than ours. So which was so cool because, you know, we made this for fun and turned out to be cited in something, you know, serious and prestigious like Nobel Prize, which is interesting. So anyway, then we said, okay, fine, let's now do it with flapping. So this is a flapping robot, if you wanna say, and this is just 1 degree of freedom. We did this experimental setup because if we flap slowly, you will not generate enough lift and you will be down here. If you flap strongly, you will generate enough lift and you will be up there. So we can generate different equilibrium positions depending on the frequency, because we want to study the effect of frequency, because vibrational stabilization is only evident beyond a certain threshold of frequency. Now we change this fixation to a hinge, so we allow the pitching motion, which is the main source of instability. So here, if we flap relatively slowly. So we're not generating enough lift. This is why we're down here, we're not up there. You can see that the system is crazy unstable. We have to stop after a while. Otherwise, the system will break. But from here, if you just increase the voltage to the motor, no feedback, no control whatsoever, just increase the flapping frequency. You will generate more lift and be up there, but also you will be naturally stabilized. The system is naturally stabilized. You give it a disturbance, it comes back. This disturbance is large, by the way, is 50 degrees, 50. And it's very robust. I have version of this setup in my office. Anyone comes, play with it, and it's very robust. You push it all the way, it comes back. Then we said, okay, good. Let's now do our last test and call our biology expert, Professor Ty Hedrick at University of North Carolina. He had this, an experiment with a real moth and hovering over an artificial flower, and he shoots the moth. He actually tortures the insect. And he has high-speed video cameras around, so he can give us the flapping motion and body motion. And the body motion, we have now control. We can consider the effect only of the averaged body motion or the zero mean contribution that is neglected when we do averaging. We pass it to an aerodynamic model, get an estimate of the aerodynamic moment. This is the variation of the aerodynamic moment, the net aerodynamic moment over the flapping cycles, first, second, third, during the excursion. Negative means it's opposing the motion, so stabilizing. Positive means it's destabilizing. So blue are the averaged contributions due to the averaged body motion. You can see that they are all destabilizing. So averaged body motions are destabilizing. This is in agreement with what the community has found. If you just focus on the average dynamics, it's unstable. But now look at the vibrational ones. These are the zero mean vibrations that you neglect when you do averaging. They are all stabilizing and they are powerful enough to outweigh the instability comes from the averaged contributions. So that was the conclusion, that insect flight indeed enjoys vibrational stabilization. Which is, it's a remarkable design by nature in the following sense, because insects they will flap anyway, right? Because they have to lift themselves, right? So this flapping motion is needed for something else, for something mandatory, for lifting. So this very same motion gives you stability for free without feedback as a side effect, as a bonus. So anyway, we published this in Science Robotics, and they were generous to write a commentary on it. Also, the Journal of Experimental Biology, they wrote a paper about it and so on. So this is, based on these concepts, we actually built this drone, if you want to say. So 4 elements of flapping elements. And it's pretty controllable, as you can see. It's very precise control. And it's also very maneuverable. It does somersault here and does, whatever. It's more stable, open loop, and more maneuverable, closed loop, and more efficient, stays longer in air in this size. And in fact, it's more playful because it has, you can have colorful wings. It's not, whenever we go to a competition, it gets the popular vote. Because the sound is not, and is not that, it is not less noisy, but the sound frequency is more pleasant than the sound of the drone. The drone is, the usual drone is like, this is like, something like this. It's interesting. It's more natural. Anyway, so I'm done with the first part. So let's take a deep breath, because I'm gonna switch gears completely to a very different topic on aerodynamics. This topic came out recently in this JFM paper a couple of years ago with Cody Gonzalez, a PhD candidate from our group. He's graduating this semester. And this was partly motivated by Ken Cheng, New York Times article. To those who fear flying, it's probably disconcerting that physicists and aeronautical engineers still passionately debate the fundamental issue underlying this endeavor. What keeps planes in the air? So I'm not trying to scare people who are flying soon. I have my friends here flying overseas, and I'm personally flying in a couple of days. But you know, the main claim that we're putting forward is that the current theory of flight that we teach all over the world is actually fragile. And let me let me tell you what do I mean by that and why I'm saying that. So this is the problem that we want to solve, right? The simplest problem in aeronautics, two-dimensional wing, and we want to compute the lift force, right? It cannot be simpler than this. This is not the whole airplane. This is not a three-dimensional wing. It's just a two-dimensional wing. It cannot be simple. This is what we teach in our undergrad, right? And we as engineers or applied mathematicians or physicists, we always like to go back to fundamentals, governing equations. So if we cannot solve Navier-Stokes, we can start with Euler. And luckily, we can obtain an analytical solution of Euler in this case. So this is the solution that we teach to our undergrad. The issue is, if you give me any solution to Euler, to this problem, I can always construct a special flow field, U1. U1 is not a solution of Euler, but together with U0, U0 plus gamma U1 together is a solution of Euler for any value of gamma. So this thing with gamma equals 1 unit is as legitimate as this solution with gamma equals 1 million unit. Both satisfy the partial differential equation and boundary conditions. So, okay, so it seems that we have a one-parameter family of solutions, infinitely many solutions. And maybe this gamma is not important. What is the meaning of this gamma? This gamma is actually the circulation over the airfoil, which solely dictates the lift force. The lift is rho u gamma. Rho is the density of the air, u is the speed of the wing. So you give me gamma, I immediately give you back the lift force. So ironically speaking, Euler equation cannot determine one of the most fundamental quantities in flight, the lift force. And the question has always been, what solution does nature select among this infinitely many possible solutions? So this actually caused a schism in the community at the early days of flight between the German school and the British school. The German school, who won this mathematical war, they said, let's look at these solutions. You know, it's as if you have x squared equals 4. So you have two solutions, plus or minus 2, and you say, okay, let me look at the solutions and see which one is more physical to accept. So if you look at the solutions, here is one flow field with a small gamma, the corresponding lift is small. Here is another solution with large gamma, the corresponding lift is large because lift is proportional to gamma. And in both scenarios, you'll find that the flow goes around the sharp edge, either from the lower surface to the upper surface or the other way around. And if you have a flow going around the sharp edge, it's similar to as if you're driving on the highway with your speed, 60 miles an hour or something, and then taking a sharp turn, zero radius of curvature. This can be because this will require an infinitely high curvature, infinitely high centripetal acceleration. It cannot happen in reality. We call it a singularity. So here comes the role of the very famous Kutta and Shkovsky-Kutta condition, which, so they said, luckily, there is only one solution in the family where the two flows come smoothly together from the sharp edge. There is no flow around the sharp edge from the lower surface to the upper surface or vice versa. So they said, this must be the correct solution and the corresponding lift must be the lift that nature provides. And, you know, when they, tested it, this is parental flow visualization, 1904, and this is water channel. Indeed, this is what is happening in reality. The two flows come smoothly together at the sharp edge in the steady state. So this is the Kutta condition. This is the theory that we teach to our undergrad. This is how we compute lift. And this is how every single textbook in aerodynamics discuss lift computation. The question that our undergrads luckily do not ask when we teach this, and I did not ask when I was an undergrad, is that what happens with this shape? There is no sharp edge, so there is no singularity. We're back to corner zero because all solutions are perfectly legitimate mathematically, and there is no physical condition to single out a solution. So the dominant theory that we teach all over the world and discuss in every single textbook in aerodynamics suddenly collapses. There is no theoretical model that can compute lift over this shape. And not only this shape, what about this shape? You can play. I mean, it's so we have one smooth solution at this edge, but not necessarily the other edge, and vice versa. So which solution should we pick? The ambiguity remains. And not only that, what if we have a fast maneuver like those done in the Top Gun movie, Maverick? So we're talking about unsteady flows. Here is parental flow visualization, the exact same catalog of picture. This is what they call impulsive start. So it's a fast maneuver. We know since this time, more than 100 years ago, that in an impulsive start, the flow goes around the edge, actually. And there are tens of papers in the community, they criticize the application of Cotta condition to unsteady flows. Yet the entire theory of unsteady aerodynamics, from the pioneering work of Wagner to Dorson, Bucherman series, all the way to the most recent work in the GFM, they adopt the Cotta condition in their unsteady modeling because there are no alternatives. So indeed, what we teach all over the world to our undergrads is a fragile theory. Whenever something changes in the shape of the wing or the flight condition, the theory collapses. You cannot compute lift. So this actually led to the following. When you look at Euler equation, you cannot determine lift on its own. You need an auxiliary condition, additional condition. But when you look at Navier-Stokes equation with this additional term, the friction, viscosity, we can compute lift. And I have to say that we cannot really solve the Navier-Stokes equation, but if you consider or if you accept some approximation to it. Anyway, so if you ignore all what I said and just look at this slide, zoom out and look at this, you may conclude that lift is due to this additional term, right? Because here we don't have this term, we could not get lift. We added that term, we got lift, right? And this is actually the conventional wisdom in the community, that lift is due to viscosity. And remember when we feed Euler equation with a Cotta-like condition, we get lift that is close enough to Navier-Stokes. And Cotta condition is coming from physical observations on real fluids. Real fluids are viscous fluids. So the conventional wisdom is that the Cotta condition is a viscous condition. It implicitly accounts for viscosity and friction. Pick your favorite aerodynamics book. Here is Anderson. Nature enforces the Cotta condition by means of friction. Here is Professor Ackroyd of Manchester. We fly courtesy of the air's very small viscosity. So if the air is not viscous, we will not. Yeah. Question?
Recording in progress. Okay.
Yeah, good. So yeah, he's basically saying if the air is not viscous, we'll not be able to fly. So that's the conventional wisdom in the community, that lift is due to viscosity, Cotta condition is viscous, blah, blah. And in fact, this is deeply rooted in D'Alembert paradox. Because around that time, D'Alembert solved the ideal fluid equation, Euler equation, no friction, no viscosity. And he obtained a completely symmetric solution for up and down, resulting in a zero net force. And this was not only on this shape, it's actually on several shapes. So deep down in the background of most physicists and fluid mechanicians, ideal fluids are forceless. They cannot lift an airplane. One thing I'd like to stress before leaving this slide is that around that time, we really did not know whether, we did not know that Euler equation has infinitely many solutions. And D'Alembert's zero force solution is only one solution in the family. We're not sure whether nature selects this zero force solution all the time or not. So this is the background that is known in the literature and books. Let me give you our own version of the story. But to tackle this, fundamental problem that remained open for so long time, we had to sit back and zoom out and ask simple questions first, like what is fluid mechanics? So as you all know, fluid mechanics is really just a mechanics science applied to fluids, right? So fluids is just a branch of mechanics, similar to solids, it's a branch of mechanics. It's But so mechanics is the mother branch. This is what I'm trying to say. And this mother branch can be done in one of two ways. There is the Newtonian way, which is force equal mass times acceleration, and there is the variational or Lagrangian way. And let me, give you a quick example to, refresh our memories about how to solve a problem using the two approaches. Here is a simple example. We have 1,000 particles in 3D. So in total, these are 3,000 degrees of freedom. But they are not all independent and free. They are rigidly connected so that if one moves, it drags the other. So let's say we have 2 degrees of freedom at the end. So too many constraints that leaves only 2 degrees of freedom at the end. Fine. How we solve this problem using Newtonian mechanics? Well, as you guys know, the very first step is to isolate each particle, draw a free body diagram, right? And write down the equation of motion for each of the 1,000 particles. These are 3,000 equations of motion. And we have to be patient here. Why? Because we will have to mathematically manipulate all these 3,000 equations to come up at the end at 2 equations only. Because at the end of the day, I have 2 degrees of freedom. And there is no other way in Newtonian mechanics to solve this problem without writing down 3,000 equations of motion. There is no way. This is how Newtonian mechanics works. And this approach for a continuum of fluid particles gives you a partial differential equation, Euler or Navier Stokes. On the other hand, you can describe variational mechanics the way you like. The way I like to describe it is there is a fundamental quantity that nature minimizes in every motion. Whether it's a planet orbiting the sun, whether it's a tree leaf falling to the ground, whether it's a projectile, whether it's a viola string vibrating, they all move to minimize a certain fundamental quantity. So if you manage to write down your fundamental quantity in terms of the degrees of freedom, the rest is easy. Just differentiate and equate to 0, right? You get 2 equations directly in your 2 unknowns, and without the need to write down 3,000 equations. So indeed, this is known to mechanicians. So indeed, whenever you have too many constraints, this right branch is the right branch. This is the way to go. And these 2 branches are equivalent in the sense they have the respect and status of first principles, because we engineers and physicists, applied mathematicians, we respect first principles. And despite this equivalence, there is huge asymmetry in our fluid mechanics community towards the Newtonian branch. So this is, for example, mandatory upon all graduate students in fluid mechanics. You will never find a single graduate student, whether with a master's or PhD degree in fluid mechanics, without seeing Navier-Stokes equation. It can never happen. They will never graduate without seeing the equation. It can never happen. On the other hand, this branch is rarely demonstrated. We don't teach. In fact, I made this exercise, and checking the curricula of many schools throughout the country, and I failed to find a single school from MIT to whatever. I failed to find a single school that mandates a course in variational mechanics to people doing PhD in fluid mechanics. This is not the case in solid mechanics. Right? Solid mechanicians, they appreciate the value of variational mechanics, and it's pretty common to find this course as a mandatory course for people doing PhD in solids. And in fact, I was complaining about this asymmetry to one of our prominent fluid mechanicians in the National Academy of Engineering, and he replied, the bright side of the neglect of variational mechanics must be applauded. So he's saying, yeah, of course, this is useless. We should focus on the important stuff. That's the attitude of overwhelming majority of fluid mechanicians. And this is sad, right? Because if God gives you 2 legs and you just intentionally decide to cripple one of them, that's not wise, particularly if this is the successful leg. In the sense, in the challenging problems in the mother branch, mechanics, challenging problems, relativity and quantum. There is no Newtonian mechanics in relativity and quantum. There is nothing called Newtonian mechanics there. It's only variational mechanics, right? Hamiltonian mechanics and stuff, right? So that was the useful branch when you had really challenging problems. And even in our classical mechanics, like the example I just gave, the too many constraints, here you solve a much larger system than there. So it's not wise to completely neglect variational mechanics in our way of preparation of next generation fluid mechanicians. So anyway, we believed in the value of this branch We believe this is the way to go because of the following. If the classical theory of aerodynamics that we teach in our undergrad already gives me the solution everywhere at any x except for one unknown parameter gamma. So if I manage to write down my fundamental quantity in terms of gamma, I differentiate and equate to zero, one equation and one unknown, and we're done. That was our idea. So what is the quantity that nature minimizes in every flow? Well, if it's incompressible flow, no pressure, no potential energy, so it's kinetic energy. If you do that, you get zero lift actually, which was quite disappointing. You know, it looked like back then that they are correct. This is useless and viscosity is necessary. And so it was a non-trivial question to ask. What is this magic quantity that nature minimizes in every airfoil problem? And this is, we partially solved this using probably hidden principle by or forgotten principle by Gauss. He wrote this paper, a 4-page paper full of text and wisdom, no equations. Here is the math behind it. If you have a collection of particles, here is the equation of motion for each particle. Mass times acceleration equal forces. In analytical mechanics, variational mechanics, we typically decompose forces into two categories. There is the green force category called applied forces, the force that you apply yourself. And there is the constrained force category in black, R. Constrained forces are there in nature only to ensure a given constraint. If the constraint is removed, the force will no longer be there. For example, here is the pendulum. The mass of the pendulum is constrained to move along a circle. So there must be a force whose sole role in life is to ensure this constraint. That's the force in the rod. So the force in the rod is classified as a constrained force. All right. As you can see from this example, the constrained force is usually normal to the motion in some sense, orthogonal to the motion, because it does not contribute to the dynamics. It's workless. It doesn't produce any work. It's there. Its sole role is to get you on the constrained surface. Once you are on the constrained surface, it does not contribute to the dynamics anymore, right? Having this background, Gauss asserted that the following quantity must be minimum at every instant in time. And let me walk you through it because it's quite intuitive actually. So F is the applied force like gravity, electromagnetic, divided by mass, so that's the applied acceleration. And now A is the actual acceleration. In the absence of constraints, no R, these two are exactly the same. You apply a force in this direction, you get a motion in the exact same direction. But then in the presence of constraints, we have R, non-zero R. The actual motion will deviate from the applied motion. Why? Because of the constraint. So Gauss said, fine, if the deviation is only because of the constraint, then it must be the least deviation that satisfies the constraint. So this deviation must be minimum at every instant in time. And this deviation is actually nothing but R over M, right? So it's as if we're minimizing the summation of all constrained forces squared, hence the name least constraint. And if you look at R here, it looks like a residual between the applied motion and the actual motion. So here we're minimizing the summation of residual squared. That's least squares, which was invented by Gauss himself. So in fact, he wrote this. It is quite remarkable that nature modifies free motions incompatible with the necessary constraints in the same way in which the calculating mathematician uses least squares. So inspired by his own method of least squares, he proposed the general principle of mechanics in which nature plays the role of a mathematician, solving a least squares problem at every instant in time to determine the best evolution from the current state to the next state. So one fun fact before leaving this slide, I was extremely happy when I learned that there are only 10 names between Gauss and myself, thanks to Navier, and there are other big names here like Hilbert, David Hilbert, and Felix Klein, and blah, blah. So anyway, let's go back to fluid mechanics. So this is, here is Navier Stokes, fluid mechanics. Mass times acceleration equal forces. I'm using incompressible flow, so unit mass, unit density. Like I said, if you want to do anything with variational mechanics, we need to decompose forces in the right-hand side. Viscous forces are applied forces, And interestingly, pressure forces for incompressible flows, they are constraint forces. Their sole role is to enforce the continuity constraint. In fact, if you give me a velocity field that satisfies continuity and boundary condition, then it's, in a couple of lines, you can prove that the pressure force doesn't do any work on it. So that's background. Now let's apply Gauss. Let's apply Gauss to this picture. This picture is known to mathematical fluid mechanicians. Or our only contribution is to remove the dust from, Gauss principle and just apply it here. If you apply Gauss to this picture, what does Gauss say? It says that the summation of all constraint forces is minimum, right? So this implies that the total magnitude of the pressure force over the domain must be minimum at every instant. And this is what we call the principle of minimum pressure curve. That's the new PC. And I walked you. So here is the cost function that we minimize. Following Gauss, there is the acceleration minus the force, or it is the constraint force, right? So this is the cost function that nature minimizes at every instant of time. So I walked you through how we arrived at Gauss, but at the end of the day, here is a theorem. If you give me a candidate solution that minimizes this functional, and this function is nothing but the pressure gradient, subject to continuity and no penetration, then it is guaranteed to satisfy Navier-Stokes equation. So Navier-Stokes is the necessary condition for minimizing the pressure gradient, which turns the fluid mechanics problem into a minimization, pure minimization. Why? Because if you give me a candidate solution that minimizes this, it is guaranteed to naturally satisfy Navier-Stokes. You don't need to worry about Navier-Stokes. You can just focus on the minimization. And the proof of this theorem is pretty generic. It's for whether you have viscosity or not, laminar, turbulent, it doesn't matter. 2D, 3D, it doesn't matter. In fact, you can have any arbitrary viscous model, viscous stress, Newtonian fluid, non-Newtonian fluid. You can have additional forces, electromagnetic forces, still the principle is valid with the exact same statement. The total magnitude of the pressure force over the domain must be minimum at every instant of time. So now let's go back to our problem that has been waiting for a while. The classical theory that we teach to our undergrad already gives me the solution. There is only one parameter that is unknown. I need to get this parameter. Fine, so we're gonna call our quantity that nature minimizes at every instant in time. And we're gonna substitute by this solution that we have from undergrad here in this coast. So this is steady, no variation with time. And because the solution we have from our undergrad is potential flow, so no viscous stresses, no viscosity. So our cost is just, the square of the convective acceleration. This is a measure of curvature, by the way. We can talk about this later. But you can take my word that this is curvature, the total curvature in the system. And because we integrate over space, the result is only a function of gamma, our parameter. And it's super simple. It's a fourth order polynomial in gamma. So really high school calculus. Differentiate this with respect to gamma and equate to 0, solve for gamma, that's it. So we said, okay, let's do this for the problems for which we know the solution already, sharp-edged airfoil. This is the variation of the cost versus gamma at different angles of attack. At each angle of attack, there is a unique gamma that minimizes curvature in the system. And these minimizers, they coincide exactly with Kutta's values for this case of a sharp-edged airfoil, which means that we happily recover the Kutta condition as a special case. But unlike Kutta's theory, this theory is doesn't care whether we have a sharp edge or not at all. So for the first time, we can consider a family of smooth shapes parameterized by this parameter D. D equals 0 is the sharp-edged airfoil. I'm zooming here. D equal 1 is the green circular cylinder. In between, we have a family of smooth shapes for which the current theory is not applicable. We cannot compute lift for that, right? So here is the contours of the cost function, the curvature in the gamma D space. Yellow curve is the minimizing gamma normalized by gamma Kutta. So if you have a specific value for D, this means it's a particular shape. And for this particular shape, we have infinitely many solutions for gamma, but nature selects only one, the one that minimizes curvature in the language of Gauss. So for D equal 1, it's a circular cylinder, the minimizing gamma is 0, recovering the well-known fact that circular cylinder is non-lifting. However, if you go the other end of the spectrum, D equals 0, sharp-edged airfoil, the minimizing gamma, normalized by gamma Kutta, is 1. So we recover Kutta condition as a special case. So far, only the two ends were known, but this new theory covers the entire spectrum from 0 lift over circular cylinder all the way to Kutta's lift over a sharp-edged airfoil. And because Kutta condition is a special case of this new theory, and this new theory, you saw that the viscous term goes away. The viscous term is not there. So this new theory is inviscid, it's non-viscous. And the Kutta condition is a special case of it. So it cannot get viscosity on its own. So the Kutta condition is not a viscous condition. When we published this, it created a nice discussion in the community. So Aerospace America made an interview for it. So they interviewed Dr. Paul Bevilacqua and myself. Paul is a former chief engineer, Lockheed Martin. He's the one who was responsible for the development of F-35. And they published this under interesting and provocative title. You think you know lift? Better read this. One last slide. This topic has an amazingly rich history, which is presented in detail in David Bloor's masterpiece, Enigma of the Aerofoil. It's a 550 pages book that tells this very interesting story from the eyes of a sociologist who relates the evolution of the theory to the underlying incidents of World War I politics and press between England and Germany. I read this book in detail and I summarized this in a two-part lecture online, available if you're interested, under this fancy title, A Mathematical War in the Background of the Great War. So conclusions, insect flight indeed enjoys vibrational stabilization. And here is the principle that we derived, the principle of minimum pressure gradient, that states that the magnitude of the pressure gradient force over the domain must be minimum at every instant of time. And when we apply this to the airfoil, we discover that the curvature is the quantity that nature minimizes in every attached airfoil problem. And using these tools, we developed a new theory that generalized, new theory of lift that generalized the Kuttas. But unlike Kuttas, this one is derived from first principles, Gauss principle, and it's arbitrary for applicable. It's applicable for arbitrary shapes, not necessarily those that are confined to sharp-edged airfoils. And it actually implies that the Kutta condition is not a viscous condition, and this creates, some schism in the community. I'd like to thank our group, of course. Cody is graduating soon. Laura just graduated. Shubhag is graduating soon. Support from National Science Foundation, Air Force, and NASA. And thank you so much. Any questions?